Hi, everybody. My name is Tamara Bonaci, and I'm an assistant teaching professor at Northeastern University in Seattle. And in my everyday, I spend a lot of time teaching privacy engineering tools and PPML and doing research around it. And so today, just a teaser on stuff around machine unlearning in the federated setting. So obligatory slide on, obligatory slide on the right to be forgotten. So a variety of legislation and legislative frameworks around the world in the last 5, 6, 7 years have enacted and put in the law the right to be forgotten. Some examples of such legislations include GDPR, CCPA, APPI, CPPA. APPI is a privacy legislation from Japan, and CPPA, the legislation that is currently in the works in Canada. And so all of these regulatory frameworks have something in common. They give the right to us as individuals and entities to request our data to be forgotten. And this, from the privacy perspective, is a great thing. But it comes with a challenge for us as privacy engineers and privacy practitioners, because it actually means two different things. It means remove the data from the data set, but also remove the effect or complete influence of that data that needs to be forgotten from any machine learning model that has been trained using the data. And that's a pretty significant challenge, one that if we lived in an ideal world would be relatively easy to solve, right? We would, every single time we get a request to remove the data, we would go back to the drawing board and we would retrain our machine learning models without the data that we're not supposed to use. In practice, that's never going to work out. It's never going to work out because big companies present here probably get on the order of thousands of requests to remove the data. And for large language models, we don't even have to be working with LLMs. Retraining the data for just one user would be infeasible, and the whole thing falls apart. But there are other challenges in addition to practicality of it. And so all of this leads to the need to do things a little bit differently, and this is where machine unlearning comes. And so machine unlearning is this sub-area of privacy-preserving machine learning that focuses on how do we actually remove the effect of the data that needs to be removed. And in principle, the idea is relatively straightforward. You started out with the original data set, and you received a request to remove some data from that data set. And so now, what you want to do, you want to take your already trained model, and you want to manipulate that trained model or the underlying training data that is used for that trained model so that you get this unlearned model on the right. This unlearned model, in theory, should behave pretty much the same as if you actually retrained your machine learning model without the data that you're supposed to remove. So they should be, these two models, the retrained one and the unlearned one, should be as similar as possible. And because I come from academia, as similar as possible can mean whatever you want it to mean. Well, not quite, but there's still quite a bit of flexibility. So what does this as similar as possible means? Going back to the theory, right? In practice, we would like to have a naive retraining process that I already said is not going to be feasible, right? We receive a request, we retrain the model, and we declare victory. No data being used, no data influencing our model. We can't do that. So we have to do something practical. And something practical, the first practical approach is a exact machine unlearning, which would be the unlearning process where our retrained model and our unlearned model are statistically indistinguishable with respect to their underlying probabilistic properties, so underlying probability distributions of both of the models. In practice, even that is too expensive of a requirement for us. And it's too expensive because it expects too much and it requires too much of an unlearning to happen. And so we can achieve it for some simple models, for small amount of data, for some pretty structured models, but in practice, it doesn't really work. So what we actually need is an approximate machine unlearning, where we have a couple of variants of it, but the point of this approximate machine unlearning process is that we're not trying to match complete underlying probability distributions of the unlearned model and the retrained model. We're just trying to match their, basically their outcomes, so their final effect. And if we can do that, for most practical purposes, that's enough. And so in terms of similarities and how do we figure out are things similar or not, this area has exploded in terms of research papers published over the last couple of years. So a variety of different metrics have been proposed, but the one that is referenced quite a bit is the certified removal metric proposed by Guo and his team. And I'm including this obligatory equation here. I'm not even going to define the parameters. I'm including it here because it's going to remind many of you to the definition of differential privacy. And that's not by accident, but this equation actually has a point. And the point that I'm trying to bring with it is that the similarity between certified removal and differential privacy here is poignant and a little bit misleading. So if you have differential privacy guarantees on your machine learning model, then you're golden. You can say that you have machine unlearning and you can achieve it. But for the most part, even with a very significant privacy budget, and very significant, I'm talking about epsilon being 18, you are not achieving, you are losing accuracy, and you still can't achieve machine unlearning. So differential privacy gives you a necessary condition, but not sufficient in this case. And that's why, even though equations are similar, they're not quite the same. So what happened in the space of machine unlearning over the last couple of years? Well, people have written all kinds of different papers around it, surveys and alike. And so a couple of things that are worth paying attention to. So if you want to design a machine unlearning algorithm, then a couple of requirements come to be important for you. First one being consistency. What you want to achieve is that your unlearned machine learning model actually behaves as similar to the retrained model as you can achieve it, our similarity. But that's not enough. In addition to the similarity between these two models, you still want your unlearned model to be accurate on your testing data and when you release it in production. You want to, in many circumstances, you want to be able to prove that you have actually unlearned the data that you were requested to unlearn. And whenever you can, you want to have provable guarantees on privacy. And by the way, not to mention, you want to have efficiency here. And so all of this in a centralized setting. When we add just a little bit of complexity to the equation, and when we start talking about federated learning, all of this in terms of complexity increases by a couple of orders of magnitude. So what are some challenges that federated learning brings? Federated learning, as is probably familiar to all of you, and I'm struggling a little bit with this, is a distributed learning approach that all of us in PPML really like because it is an approach that allows us to jointly train a machine learning model such that every single client holds their private data set and they are never releasing the data to anyone else. What they're doing is they're releasing the updates of their local model training to the centralized server. The centralized server generally aggregates those updates, sends the feedback back to each of the clients, and eventually when all of the clients converge to the global model, we declare victory and we have a trained model. A couple of challenges with federated learning. So first thing that we like from the privacy perspective, the data subset held by each client is private. But data subset also generally isn't identically IID. And that becomes a challenge because a lot of the approaches that we use for machine unlearning do assume IID. Additionally, when it comes to federated unlearning, all of the requirements that we had for machine unlearning in a centralized setting still apply, but we still want to maintain the privacy of each subset on the client's local storage space. And so when you add privacy that you started out with and privacy that you want to preserve, in the federated unlearning case, things get a little more complicated because of a couple of challenges. So challenge number, let me click through. Challenge number one that we see in the federated unlearning case, now I want to go back. Okay, so first thing that happens in federated learning and then unlearning case is that each of the clients holds their own local data set. And each of the clients presumably holds their individual non-IID data. However, with every local update and with every iteration, the influence of that local model updates propagates to all of the other models. But not every client contributes their updates in every iteration. Not every client is even present in every iteration. And so we have this very stochastic knowledge permeation in federated unlearning, which makes it extremely difficult to start even approximating and reasoning about the influence of the individual data set. On top of that, because each client holds their data privately, data is rather isolated on each client, and trying to measure the influence in using the same metrics we would have been able to do in the centralized setting becomes rather complex. The added complexity to that is that we now have a question of who is supposed to unlearn. In this decentralized setting, we have a client who may trigger data removal. We have a server who may trigger data removal. We have a client who may trigger data removal and then remove themselves from the equation as well and not help in any way. Or a client who will trigger just a partial data removal, like we've seen on the previous slide. The question that goes beyond that is, what is supposed to be unlearned? Are we unlearning the entire client's data? Are we unlearning a specific class of data from all of the clients that are present? Are we unlearning some specific sample or feature? And all of that adds to the complexity that we've started addressing it. Some algorithms have been proposed. For the most part, we can break down the algorithms proposed for federated unlearning into passive unlearning approaches, which are the approaches where the client who triggered the removal actually removes themselves from the equation as well. And here we're generally talking about two broad approaches: server standalone unlearning and client-aided unlearning. And active approaches, where the client who triggered the removal generally stays present and tries to help the process. The approaches exist, but as you can see only from this very high-level teaser, what has been addressed so far is the scenario where a client triggers the removal. We still haven't even touched the idea of server triggering removal completely. We haven't even started thinking about how might be actually provide a proof of removal in the federated setting. How would we allow someone to verify, even if that someone is just a client who triggered the removal? Not to mention that the statistical properties of the client in the federated setting, the fact that they can join and leave the system whenever they please, the fact that they are not contributing the data in every single iteration, changes the mathematical model of how we're doing things rather significantly. On top of it all, we have a privacy threat. It turns out that model inference attacks work in federated learning as well. If a model standalone can unlearn the client's data, then the attacker can learn all of the other client's data as well. And so with this, some ideas and some teasers for what's out there and waiting for all of you good people to work on before we can actually use it and deploy it. So thank you. Happy to answer questions you might have for me. Thanks.